Then the next speaker deals with the activity cycle of HAP 11, Brett Morris from Washington. Go ahead.
It is on. There we go. Okay. All right. So yesterday we heard great talks about many, many stars, and I'm going to do the exact opposite and tell you about exactly one star. And that one star is HAP 11. Throughout my talk, I want you to think about one question, which is, what would happen to the solar dynamo if you took 20% of the sun's mass? How would the solar dynamo change? The convective depth would become deeper. The tachocline might be deeper. How would that affect the surface expression of spots on the surface of the star? In order to answer this question, I'm going to first just review some properties of the solar activity cycle that we're going to uncover on HAP 11, and then tell you how its transiting exoplanet gives us information about its star spot distribution, and then follow that up with some ground-based observations. If we look at the sun, I'm going to preach to the choir here for a moment. The sun has active latitudes near plus or minus 15 degrees. These active latitudes vary as a function of time throughout the solar activity cycle, giving rise to the solar butterfly diagram as we've seen, which shows that spots emerge at high latitudes and move towards the equator. Ideally, we'd love to be able to see something like this on another star someday. And with HAP 11, we can almost get close. HAP 11 is a K4 dwarf. It's 80% the mass of the sun and has a rotation period of 29 days. Unlike the sun, it has a hot Neptune, which orbits at a 5-day orbital period. And that hot Neptune acts as a really poor coronagraph, blocking out just a tiny portion of the stellar surface as a function of time. And as we observe with Kepler, we can collect photometry, and even though we don't have this beautifully resolved view, which is of SDO images with a HAP 11-like planet superimposed over the star, you can imagine that as the planet passes over the spot, the transit light curve that we would observe is perturbed. Less light is missing when the planet is passing over a dark star spot, and so you get a positive bump. The amplitude of the bump tells you something about the spot contrast relative to the mean photosphere. The timing of the bump tells you something about where on the stellar surface the spot is located. But even better than that, HAP 11 is a doubly lucky system because the hot Jupiter, hot Neptune, is misaligned significantly. We know this from Rossford-McLaughlin observations. And so it eclipses from nearly the southern pole to nearly the northern pole of the star, giving us a slice in longitude at many latitudes, which allows us to instead probe with each transits of spots in both active latitudes. That's how you go after studying a butterfly diagram. So for this one star, we can try to get a deep view into what its dynamo is doing. Here's what the actual data look like from Kepler. My microphone does not want to work. Can you hear me? There we go. So actual data from the Kepler Space Telescope of HAP 11 with 1-minute cadence looks something like this on the right. And on the left is our inferred spot distribution using software called STSP, written by Leslie Hebb and Graham Roan, which models each spot as a circular spot with a fixed contrast, but allows the spot's position and size to vary across the surface of the star in order to best fit a transit light curve. We use Markov chain Monte Carlo to vary these positions and sizes so that we can infer the degeneracies between these parameters for all of the transits over the entire Kepler mission. And we're able to build a spot map of HAP-P11 throughout the Kepler mission. This is a cumulative spot map, so this is not that there were this many spots all at once, but this is how many spots we observed throughout the Kepler mission. If I collapse this map down to one axis, the one axis you would want to see is the latitude distribution of spots. And we see that spots cluster around 16 degrees in latitude, just as they do on the sun. There is a significant asymmetry between the northern and southern hemispheres. Feel free to ask me a question about that later. Because the planet is transiting from the south to the northern pole of the star, we get an almost unbiased view of the entire stellar surface because we're getting a slice in longitude at many latitudes. And so we can say something about what the total spot covering fraction is based on the spot coverage in transit. And we find that the spot covering fraction on HAP-P11 is something like 100 times greater than the spot covering fraction of the sun. That being said, the spots themselves are not so different from sunspots. We can measure the radii of the spots compared to the radii of sunspots, which is outlined here near solar maximum in black. And we see that the mode and distribution for HAP-P11's spot radii in physical units matches up with the sun's, which indicates that the small-scale physics is likely doing the same thing on HAP-P11 as it is on the sun. So not only does the dynamo seem to operate in the same way in that we have active latitudes of 15 degrees, but the spots are the same small-scale magnetic features. So to summarize, we've got a similar latitude distribution and similar physical radii, but 100 times more spot covering fraction on HAP-P11, but a solar-like dynamo. Now, in the second half, I'm going to talk a little bit about some ground-based follow-up that we've done since. Because the next thing we would like to know is, does it have an activity cycle like the sun? And one way you could go after looking for the activity cycle is measuring the calcium H and K S index, as we saw in Ricky's talk. And we find that we have not yet observed one full period of the S index. And so it's impossible to say what the cycle period is for this star. But what we can say is that the Kepler years, which were outlined here, were during a time of relatively high S index. And so maybe we were observing with Kepler near active maximum. Another question that we want to ask is, how normal is HAP-P11? It seems to have 100 times more spotted area than the sun. Is that usual for K-dwarfs? To answer that question, we can look at R prime H and K, which is a normalized version of the S index, the proxy for chromospheric activity. And we can compare HAP-P11, which is this purple square, to stars of similar effective temperature and similar rotation periods, which is in the box here. And we see that HAP-P11 is more chromospherically active than its peers of the same rotation period and similar spectral type. And we wonder if that might be due to the planet. This planet is on an eccentric orbit, significantly misaligned. And so those of you out there who study planet-star interactions, I'd be really interested in your opinions on whether or not the tidal interaction of this planet can influence its star. Second to last, we are continuing to measure transit photometry from the ground. It's significantly more challenging to do from the ground, but we have a trick up our sleeve in the form of a holographic diffuser, thanks to some great work by Gumi Stephenson and the team at Penn State. And we are able to continue measuring spot occultations from the ground and found recently that HAP-P11 is more spotted than ever. And lastly, one technique that we can use, which covers the entire surface of the star, which the previous techniques were limited to the transit cord of the star, is to study the Echelle spectra of the star as a whole and model the spectrum in TIO absorption features as a linear combination of a hot star and a cool star atmosphere. And that way we can try to see what the total spot covering fraction is on the star, even outside of the transit cord. And we find in several bands consistent spot covering fractions with the spot covering fractions inferred in transit. And so HAP-P11 is a really great benchmark system for studying solar-like activity on a K-dwarf. I think I want to highlight that we've used a number of different techniques to study it now, and it appears to have the same spot covering fraction no matter how you look at it. And I look forward to your questions, but before I end, I want to say that that was the first half of my PhD work, and I'm finishing up my PhD now. This is the rest of my PhD work. And so I've been doing a lot of things, and I would love to talk to you about all of the other things. So in questions and at lunch, please come up and talk to me about anything else in addition to Happy 11. Thanks.
Well, thank you very much, Brett. Are there any questions? There in the back. Second.
Very much. Okay, this is working. Hello, Katja Poppenheke, Queen's University Belfast. Really exciting work, wonderful. I was wondering, is it possible to identify from the data you have recurring occultations of the same star spot and maybe even identify spot lifetimes from that?
That's a great question. The challenge in identifying repeated spot occultations is that the active latitudes are active latitudes. And so identifying the same spot is tricky because all we're seeing is a bump in the transit light curve. And we know that the spots are likely to occur at the same latitude in the next transit because there's an active latitude there. And so really there is no way that we can identify for certain that the same spot is being occulted.
Ben Brown, University of Colorado. This is a question either for you or for the audience. Are there differential rotation measurements for HAT P11, or is there likelihood of getting those for HAT P11?
There are no differential rotation measurements from my work, and part of the reason for that is the degeneracy between spot position on the transit cord. Every spot could be on either side of the transit cord and would give you the same signal on your transit light curve. And as a result, it's impossible to really measure differential rotation for this star. There are other stars like Kepler 17, which are well aligned, and spots falling on either side of the transit cord can give you some hint as to the differential rotation. And so I would point you to Jim Davenport's thesis for a measurement using this technique to measure differential rotation.
Gabor Basri, UC Berkeley. That's really great work. My question is, what's the photometric amplitude of HAT P11 compared with similar K stars, and is there a way to relate that photometric amplitude to the spot covering factor that you've gotten another way?
Yeah, so the photometric variability, if you were to look at the Kepler light curve on long timescales, is about 3%. 3% is not that big and it's not that small. It's kind of somewhere in the middle, right? We see super flare stars that are that have much higher amplitudes, and we see other K stars that have smaller amplitudes. Part of what we're seeing, I think, is that this image is meant to be to scale and realistic as to how many spots are actually on the surface at a given point in time. And so as one spot rotates off, another rotates on, and the total variability is actually relatively small.
Over here, Pierre Maxter, Keele University. Just two quick comments about this is a really nice talk. This is a really nice.
We said questions.
Yeah.
Formulate your comments and ask questions.
Okay. This is going to be a tough question then. HAT P11 is unusual in one sense, in that it's actually very dense. It sits below the isochrones. Do you have an explanation for that?
No.
No? Here.
So I'm Rashid from MPI for Solar System Research. So given that its rotation period is similar to the Sun, I would expect that the flux tubes, if they are rising from the interior, would follow more or less radial trajectories. So I think in that sense, it would be correct to say it's a solar-like dynamo. because what you see is what you must be there in the interior, in terms of latitudinal information. However, have you ever done numerical simulations with mock spots distributed all across the surface? I mean, especially around the poles. If there's a polar spot,
question, please.
Excuse me. Yeah. Such a nice work. So, what if there's a polar spot? Can you detect it? I mean,
so we are not sensitive to this part of the pole and to this part of the pole using the transit photometry technique. However, if there were large polar spots, they would show up in the TIO absorption modeling, and we don't see them there.
Yuta Notsu from Kyoto University. My original question was the same as Gibor, so I ask another question. Are there any other plans for future observations, continuing the whole long-term changes?
There are, and they are my plans to just continue observing the star. I think we should continue observing, which I know the Keck-Hires folks plan to continue to observe in case there's a long period planet to measure the RVs. So I know that there will be a good source of continuous high resolution spectroscopy that we can use to measure its activity cycle, in addition to more diffuser assisted photometry from the ground.
Last question.
Thank you. Travis Metcalf, Space Science Institute. Presumably the 29-day rotation period is from the long cadence light curve that spans most of 4 years. And so if there is spot migration during those 4 years, it ought to be possible, to answer Ben's question, to put a limit at least on the differential rotation.
I can show you a figure that is tempting but dissatisfying. If you were to look at the sun, this is the spot latitude distribution as a function of time over a 4-year bin. You see evolution. If I show you the same plot for HAPI 11, it's not obvious that there is a distribution shift in the mean latitude as a function of time over 4 years. And so it's plausible that differential rotation could be picked up by noting where the spots are and the rotation period, and separately by measuring the drift in latitude as a function of time. But the baseline was not long enough to measure any change in latitude as a function of time.
And did you want to comment on the hemispheric asymmetry?
Sure. The hemispheric asymmetry is...
But please, concisely.
Yes, as concisely as possible. If you look at the sun on a 4-year timescale, each hemisphere kind of kicks into its activity cycle at a slightly different time. And so if you were to look at the sun during these 4 years, for example, the northern hemisphere turned on before the southern hemisphere. And so what I think we're observing is natural variance within where we're sampling and not an observational bias in favor of one hemisphere instead of the other.
Okay, thank you very much. I have to apologize. There were four more hands that I couldn't call up. So please, grab Brett at a later time. But we're running over time already. And last